Okay, good afternoon, everyone. First, I would like to thank the organizers for giving me this chance to present our work done at Phuket Rio. But before my talk, I would like to mention that we at Phuket Rio, we are constantly looking for colloquial speakers. And if any of you happen to stop by in Rio de Janeiro on the way back, please let me know. Okay, so basically today, my talk is going to be about this notion of quantum metric or quantum geometry in general. And I would like to share with you our research recently about how to link this notion of quantum metric to various dielectric and optical properties of semiconductors. And then having this as link established, we can use it to in turn to propose this optical detection of a very important quantity in the density functional theory, the so-called spread of one-year functions. And then I turn to superconductivity, and I would like to share with you how this notion of quantum geometry is also related to the most defining properties of superconductivity, namely the Meissner effect, and propose what we call the superfluid wave marker that can describe the Meissner effect under the influence of disorder. And this work is the part of a semiconductor work is done mainly with my student Luis Castillo, who is here in the conference, and the experimental part in collaboration with Professor Lázaro Ferreira's group in Phuket, and mainly done with our postdoc Shai Zhang, who is now back to China. And the graphene part of my talk is mainly a collaboration with Professor Dennis Kohan, who is now in National Chong Kung University in Taiwan. And also the superconductivity part is hard work done with my student David Poyes, who is also now here in the conference. Okay, so since I will be talking about the quantum geometry, so first let me introduce this notion of the quantum metric, and especially within the context of semiconductors. So what you do is the following. Suppose you have some n minus number of valence band states. Now, because they are all fermions, so if you would like to construct a single state that satisfies the fermion statistics, then you use this fully antisymmetric Slater determinant state of this combination of all these valence band states here. Now you can think of this valence band state as a unit vector in the many-body Fock space, right? So if you change from a specific momentum k to a slightly different momentum k plus delta k, then it's like this unit vector is going to rotate from one direction to another slightly different direction. Now imagine if you take an inner product between these two states, then it's kind of like you are counting the cosine of the angle between these two unit vectors. Now you do an expansion to leading order in this small delta k you have moved, then the coefficient in the front is what we call the quantum metric. Now you can imagine that this thing is going to be related to the Taylor expansion of the state that you begin with. So, and the particularly important element is the diagonal element of this metric, which is given by the momentum derivative on your valence band states in this way. And you can also express it in terms of the original valence band state, which I call it n, and the conduction band state, which I call it m. And the result is that you are summing over the derivative of momentum on the valence band state product with the conduction band state. Okay, so why is this thing important? Because it turns out that over the years, people have realized that the real part of optical conductivity in semiconductors is actually related to this quantum metric, the spectral function of this quantum metric multiplied by the frequency. So this is the usual expression of a real part of optical conductivity. And as you can see, basically this optical transition matrix element is precisely this quantum metric that I listed above, with a multiplication of delta function just from the Fermi-Golden rule argument. And then there's a multiplying by frequency just from the Maxwell's equation. Yeah. Okay. Yes. No, this is for any momentum in your entire Boolean zone. Sig. Yeah. Oh, these are all depending on momentum. So I am only talking about a specific momentum now, and in the next slide, when I talk about the properties that you actually measure in real space, then you got to integrate over the momentum, as you will see now. So here I'm trying to argue that I'm trying to link these properties to the experimental measurables. So I do the following. So how do you discuss the propagation of a light in the semiconductor? Well, you start from the wave equation, right? And remember that all the complications in the semiconductor is embedded in this complex dielectric function, which you often write it as a square of the complex refractive index. Now there are two different ways you can interpret this dielectric function. You can think of that the electric field, the oscillating electric field of light, will cause the positive and negative charge inside a semiconductor to oscillate with time. And this way amounts to a frequency-dependent charge susceptibility. Or you can think of it as this oscillating positive and negative charge as an oscillating charge current, right? And this amounts to the definition of an optical conductivity here, divided by frequency, and there's a factor of I there just from the Maxwell's equation. And then few words about this refractive index, which squares will be the complex dielectric function. You know the real part tells you how the speed of light is slowing down inside the semiconductor, and it also tells you how the light is bending when it enters from the vacuum to your semiconductor. And the imaginary part tells you the so-called absorption coefficient, which tells you how long can the light penetrate into this material. Okay, and then there's another thing that's important here is the reflectance, which you got by matching the electromagnetic wave at the interface between the air and your semiconductor. And it is expressed in terms of this complex refractive index in this way. And the transmittance is nothing but 1 minus this reflectance. Now the reason that I'm spending the past 1 minute to tell you all these quantities that you have already known in the electrical merming is to emphasize that they can all be expressed by the optical conductivity, because you see that one of them is related to the other, right? So all of them must be able to express in terms of both the real and imaginary part of optical conductivity. However, you also know that these two are not independent from each other because there's a Kramers-Kronig relation between them, right? And therefore, I come to this very simple conclusion that the optical conductivity I have told you in the previous slide, which is defined with respect to a specific momentum, but all these properties are measurements in real space in the bulk big chunk of semiconductors. It's nothing but all these ones, but integrated over momentum. Yeah. And then, but the key point is that the quantum metric still remains there in the real part of optical conductivity and in the imaginary part as well. Because from here to here, you simply use a Kramers-Kronig relation, which will make the delta function to become some other energy frequency-dependent kernel, right? But the quantum metric itself does not depend on the frequency, so the quantum metric remains. As a result, yes. That's a good question. So since I know that this conference has a lot of strongly interacting people, so the short answer to your question is you can put all your interactions into your optical conductivity here, your conductivity particle bubble. Yeah. From there, you can dress it with whatever phonons, impurities, whatever you like, and still divide it as a function of frequency to define a spectral function for this quantum metric, which I call it the stressed, I call this the stress quantum metric spectral function. Yes. Are the conduction band energies and valence band energies. Well, if you wanted to do that, then you really have to do the particle hole bubble and take the imaginary part. True, here is a proposal, and this proposal is consistent with what you can measure experimentally. Yeah, so we call this the dressed quantum metric spectral function. Okay, but just to finish my argument here, So here I'm trying to argue that both real and imaginary part has quantum metric there, and therefore all these effects, all these optical and dielectric properties I'm telling you here are quantum geometric effect. So next time you take a piece of semiconductors, you put it under the red light, it appears darker than put it under the green light, and that is because the quantum metric has some, these two different frequencies are different. Yeah. Okay, and now I would like to in turn ask the following question. Then does it imply that we can actually use some optical effects to detect the quantum geometry in the block bands? Yeah. So for the sake of my argument, I would like to consider this momentum integration of the quantum metric over the entire Brillouin zone. And I call this a fidelity number, and this has already been considered in literature in many different places. The earliest is by Mazzario and Vanderbilt. Now this thing is important because it turns out to be related to the so-called spread of one-year functions. So the argument is like this: you take your block states and Fourier transform it to real space, and you get the one-year functions, right? And these one-year functions are all localized in the position where you specify them. And you can define the so-called spread of one-year function, which is essentially the second cumulant of the position operator of this one-year function localized at whichever point you like. And so it basically tells you how spread out is your one-year function in real space. Now this thing can be separated into two pieces. One is the gauge invariant part that is called omega I, and the other one is the gauge dependent part that is called omega tilde. Now the big business in the density functional theory has been how do you choose a smart gauge such that you can minimize this omega tilde as much as possible, and leading to the so-called maximally localized one-year functions, right? But this is not my concern here. My concern is more about how do you experimentally measure this gauge independent part, omega I here. And it turns out that by Souza, Wilkins, and Martin in 2000, they have proposed that this thing is nothing but essentially the trace of this fidelity number, or essentially just the fidelity number. Yeah, so that's very nice. So it means that if you can manage to find some way to measure this momentum integration of the quantum metric over the entire Brillouin zone, then you can get the spread of one-year function. Now, okay, the question is how do you detect this? Now, coming back to this formula between the relation between the complex dielectric function and the optical conductivity. So from the previous slide, you know that exactly what you need is the optical conductivity divided by frequency and then integrate over frequency. And it turns out that this is nothing but the imaginary part of the complex dielectric function. So our theoretical proposal is this: you take the imaginary part of optical conductivity, imaginary part of dielectric function, measure over the entire frequencies range, which has been measured since the 60s by means of the so-called ellipsometry measurements. Yeah. You integrate it over frequency, multiply by this numerical factor, which comes from a conversion of a bunch of fundamental constants, multiply by the unit cell volume and divide by angstrom, you get exactly the spread. Now the power of this formula is that it has no fitting parameter. You take the experimental data, whatever it is, you want to measure, integrate the area times this number times the unit cell area, done. Then you get the spread. Now using this protocol, we have extracted the spread of one-year function for silicon from this experimental data is without any calculation, yeah, unbiased. Is about 68, for germanium is about 83, for bismuth telluride, which is a 3D topological insulator, and surprisingly, it has already been measured since the 60s. The spread is about 407. Yeah. Okay. Yes. No, it's, you see, it's in angstrom square. Yeah. Or you can also divide it by unit cell area. Then it gives you this what I call the fidelity number, which is the momentum integration of quantum metric. Then it is this number is over here. Yeah. Roughly speaking, yes, yes, yes. So you see that, yes, it is like this. So this dimensionless number will, actually it's not dimensionless. It will basically tell you how much does your block state is changing in your Brillouin zone in absolute scale. Okay, now I'm done with 3D. To draw more relevance with this conference about 2D materials, how do you do this in 2D? Well, in 2D, the dielectric function is not really a relevant quantity, but you can ask about the absorption or absorbance of a 2D material. So take a piece of 2D material, put it on a transparent substrate, you pass the light in through it. The absorbance in the visible light range is basically the opacity of this material, right? So how do you measure the, what is absorbance exactly? Well, you calculate the absorption power of the light by this 2D material, which is essentially given by the real part of optical conductivity times the field square. And the absorbance is nothing but this power divided by the incident power of the light, which is nothing but the Poynting vector times the unit cell area. And then you get still the frequency multiplied by the what I call the fidelity number spectral function. So in 2D, the concrete experimental protocol is that you take your absorbance, divide by frequency, and then integrate over frequency, and then multiply by the area of the unit cell. Then you get the spread of one-year function. And once again, there's no fitting parameter. Okay, applying this to graphene, then you got something that is quite interesting, because graphene is known to have a frequency-independent absorbance at low frequency, right? So if you divide by frequency, integrate over frequency, you got logarithmic divergence. It turns out that this tiny gap caused by the intrinsic spin-orbit coupling of the order of 10 to the minus 5 electron volt actually saves you to have a finite spread of one-year function. And the number that we got numerically is about 2.36 times the area of the unit cell. And yeah, so that's for graphene. Now, to draw more relevance to this conference about twisted bilayer graphenes, I'm sure that, so we have already heard a lot of theories about this, right? But one of these theories is saying that the superconductivity in these materials is because of the quantum metric of the flat bands. Yeah. Especially promoted by Professor Torma and Professor Bernavik. Okay, is this true? I don't really know, because there are many competing theories, but our interest is more about, can we optically detect this quantum metric of the flat bands? Yeah. So to examine this idea, we do the following. So we take this model by Bennett et al., which is a simple type binding model that claims to be able to explain the band structure of a twisted bilayer graphene over a very wide range of twisting angles. And now their magic angle is around 0.99 degree, and this is their band structure here, and you see that this is relatively flat in a very large area of the Brillouin zone. We calculate the profile of the quantum metric, and it peaks at K point, M point, and so on, and so on. Yeah. So we also calculate the absorbance out of this model, and it looks like this. It peaks, basically has a peak that peaks around the energy difference between the two flat bands around a very large area of the Brillouin zone. Because these two flat bands are more or less separated by the same energy difference, so you see that the absorbance will show up at the peak that is peaking at this energy difference, right? And in our calculation, it peaks around 3 milli-electron volt or so, which is in principle measurable, although you have to use a very different light source, because the 3 milli-electron volt is falling in the range of millimeter wave. Yeah? But in principle, it's measurable. So what we're saying is that suppose you do this, you measure its absorbance as function of frequency in this millimeter wave range, and then you take the spectrum divided by frequency, you're gonna get what we call the fidelity number spectral function that will still have a peak there. And then you integrate this peak area, then you get precisely the quantum metric of the flat bands integrated over the entire Brillouin zone. Yeah. And this quantity is also related to the spread of the one-year functions on the Moret superlattice. So this, so all this can be measured. So what we are saying is that it's true. Actually, in this model, if I remember correctly, they have included interactions. Unless you define it from the optical conductivity. Yeah. I'm sorry? But dress the free fermion, dress fermions. Now, if I have this conductivity bubble and then I dress it with whatever phonons, impurities, and take the imaginary part of this, still an experimentally measurable quantity. And in fact, I can take my silicon and put in a lot of disorders and measure it again and see how the dielectric function is changing. Then this will give me exactly the information that I was talking about. Okay, nevertheless, let me continue. So, our proposal is that if you can do this experiment at different twisting angles, and if you really found that this quantum metric is enhancing at a magic angle, then that might be some evidence to support this class of theory. Okay, and then we can actually do better than this. We managed to write this absorbance to real space defined on every lattice points of a 2D model. So long story short, this is the so-called, using the so-called formalism of the so-called topological markers. So essentially, all these valence band states and conduction band states in real space, there will be just the negative energy eigenstates and positive energy eigenstates of your lattice Hamiltonian. You diagonalize it and you insert some position operators, multiply in this way, and you still have the energy conservation coming from the Fermi-Golden rule, and then you can manage to calculate the absorbance in the atomic scale on the individual lattice side. So to test this idea, we apply this marker to the WS2, which is a transition metal dichalcogenide. And using this model by Professor Dichau et al., and it is a triangular lattice model that counts only the d orbital degrees of freedom of the tungsten atoms. Yep. And then the thing that you can do is you can put in some impurities and calculate this, using this marker to calculate the absorbance on each individual lattice sites. As a function of frequency, it looks like this. So here, purple is this purple line, which is exactly on the impurity side. Now you see that the absorbance has been strongly suppressed. Now this is very intuitive, because if you put in a potential impurity there, then you're gonna expel some electrons over there, right? So there are just less electrons sitting there to absorb light, so the absorbance is reduced. However, what we found is that it recovers very quickly in the insulator, namely even the nearest neighbor side of the impurity, it has pretty much recovered to the homogeneous value. So this is very different from the metals. That's what I mean to say, because for metals, you put an impurity, there's gonna be Friedel oscillation over there, but in insulators, you don't. So the suppression is very local. And what I mean to mention is that this is in qualitative agreement with our experiment done at Phuket. So what we do is we take the WS2, we measure its absorbance, and these solid lines are the experimental lines. The blue is the pristine WS2 absorbance as a function of frequency. Now and the dashed lines are our theoretical fit, and you see that they fit pretty well, at least at low frequency part. The higher frequency part we cannot fit because these are the p orbitals coming from the s atoms, which we did not take into account. And then we take this TMD, we hit it with some plasmas to produce some impurities, and we measure its absorbance again. And then you see that the absorbance has been reduced to the orange line, which can be explained by this local suppression of the impurities caused by the plasma. And then we hit it with another more plasmas, and it gets even more suppressed. Yeah, so this is really, we can really explain this using, oh, okay. Okay, now let me use the last 5 minutes to talk about the superconductivity. Yeah. So what we wanted to argue is that it turns out that the Meissner effect in superconductors is also given by this quantum metric. How so? Well, how do you study Meissner effect using this Scalapino, White, and Jones model? They say that it's very simple. You do the usual usual minimum coupling, but this is not enough. You actually have to expand to the second order in the vector potential. And as you can imagine that this will be a second order on the derivation of your BDG Hamiltonian. And you simply take an ensemble average of this guy, then you see that it is a quantum metric multiplied by the quasi-particle energy. But this quantum metric is somewhat interesting. It is the quantum metric of the quasi-host state of the superconducting state. So take any 2x2 BDG Hamiltonian that you have epsilon k, and delta delta in off diagonal term. You diagonalize it. The wave function is the Bogoliubov coefficients that I don't bother to write down, and you calculate a quantum metric of this state. It turns out that it is exactly contributing to the superfluid weight that enters the London equation, and hence whose inverse is the penetration depth square. Now this will also mean that the ratio between the penetration depth and the Ginzburg-Landau coherence length, which determines whether the whether your superconductor is type 1 or type 2, is also determined by the quantum metric. So roughly speaking, if your system has more quantum metric, then it's more type 1, and you have less quantum metric, then it's easier to be destroyed by magnetic field, so it's more type 2. Now in my last slide, I would like to show you that these, actually you can also map this superfluid weight to real space as a superfluid weight marker. Now let me just simply skip through this slide. So this superfluid weight marker allows you to study the diamagnetic current in the presence of impurities. So in this slide, what I mean is, suppose you have a piece of superconductor and you apply the vector potential to the left. Now all your dielectric current is going to be against the vector potential, so it flows to the right. And if you don't have any impurities, then the current is a uniform flow. Now, as you put in more and more impurities, our marker allows to study the local diamagnetic current. And what we found is that the impurities cause this diamagnetic current to become a bit turbulent. Yeah? And moreover, it has this very interesting phenomena that around very strong impurities, the currents sort of circumvents this impurity. It's kind of like, imagine if you have a river that is flowing uniformly, and you put some stones into a river, then the current is kind of started to circumvent these stones. And moreover, what we found is that the overall magnitude of the average current has been suppressed by this disorder. And let me remind you that this is completely consistent with Pipa's famous experiment back to 1953. What Pipa shows is that as you put in more and more impurities such that the mean free path is reducing, he sees that the penetration depth is increasing. And this is completely in agreement with this, because penetration depth increasing means that the superfluid weight is suppressing. And correct me if I'm wrong, I do not think that this experiment has been explained theoretically in a self-consistent manner until our theory here. Okay, so just to summarize, so first I show you that all these are optical and dielectric properties, including the dielectric function, charge susceptibility, refractive index, absorption coefficient, and reflectance and transmittance. They are all quantum geometric effect. And secondly, you can use this to in turn measure the spread of Wannier function in 3D via dielectric function and in 2D via absorbance, and who is generalizable to disorder systems. And finally, superfluid weight, and this is Ginzburg-Landau criteria, are also determined by quantum metric. And finally, you have this turbulent and reduced diamagnetic current caused by disorder. And that's it. Thank you very much.
We have time, but Andre?
I can ask without from the naive question.
Yes.
But when you talk about Meissner effect in terms of quantum methods, is it just, if I can ask this way, is it just repackaging of a conventional effect of coherent factors, of Bogoliubov coherent factors? Or there is more than this?
Yes, actually, you can also write this entire thing in terms of a Bogoliubov coefficient. But it's more like a reformalism of the thing that you already know of. But now it's just to say that this combination of Bogoliubov coefficients is really having the physical interpretation as a quantum metric. And moreover, that allows you to map it to real space to calculate it directly in real space as a marker. Yeah, but otherwise it's a reformulation of something that you already know of. That's true, yeah.
Okay, let's thank our speaker.
Okay, thanks.